Welcome to Talk Sensors.
Thanks for having me back.
Yeah, of course. So if you are listening to this right now, you are likely part of that really unique audience of graduate students, engineers, and intelligent builders who are actively trying to construct the next generation of artificial intelligence.
Right, the people actually in the trenches.
Exactly. And if you are building in this space, you already know we are running into this just massive, incredibly frustrating wall.
Oh, absolutely.
So today's deep dive is an exploration into what I would call the absolute Achilles heel of modern AI, which is long horizon reasoning.
Yeah, that is the perfect way to phrase it.
We are looking at a really groundbreaking architecture today. It connects large language models, our beloved LLMs, with classical, old-school symbolic planners.
Which sounds kind of wild at first.
It really does. But the goal here is ambitious. We want to create agentic AI systems that are capable of flawless execution in complex physical environments.
And it is a critical wall we have hit. I mean, I would honestly argue it is the defining bottleneck of the current AI hype cycle right now.
Right, because right now, what's the industry doing? It's just brute force?
Exactly. The standard approach is just brute force. We just make the language model bigger. We throw more parameters at it. We throw more compute at it.
Just hoping it magically gets it.
Right. Hoping it suddenly learns how to interact with the physical world without making these just catastrophic errors. But what we are unpacking today proposes a completely different paradigm.
A total shift in how we think about agents.
Yeah. The core thesis is basically this. We do not need to force LLMs to become flawless logic engines. Instead, we can use them as natural language interfaces.
The translators?
Basically universal translators, yeah. They outsource all that heavy lifting of rigorous reasoning to specialized deterministic tools.
I really want to pause on that distinction because the context here is vital for anyone actually trying to build autonomous agents right now.
It is the whole foundation of the problem.
Right. We see these models, and frankly, they are incredible at linguistic competence. They know how to say things,
Well, they're beautiful writers.
Exactly. They have mastered the syntax, the tone, the structure, the sort of persuasive cadence of human language.
But then you ask them to do something real.
Right. When you ask an LLM to actually plan a multi-step physical task, like, say, cooking a meal, or rearranging items in a warehouse.
Or even just stacking some blocks.
Yeah, stacking blocks. They completely hallucinate physically impossible actions.
Which cognitive scientists actually call a lack of functional competence.
Functional competence, meaning they don't actually know what to say or do when the strict, unforgiving laws of physics are involved.
Yeah, the distinction between linguistic and functional competence is the central tension of everything we're discussing today in this deep dive.
Because it's an illusion, really.
It absolutely is an illusion. And if you look at the history of artificial intelligence, you can trace this illusion all the way back to early language models.
Well, like how far back?
I mean, even programs like Eliza in 1966.
Wow, 1966.
Yeah, Eliza could mimic the conversational patterns of a Rogerian psychotherapist.
Right.
I could ask you, how you felt about your mother.
Right.
So it possessed a crude form of linguistic competence, but it understood absolutely nothing of the underlying reality of human psychology.
It was just matching patterns.
Exactly. And today's models, even the most advanced ones, with trillions of parameters, they actually share a piece of that DNA.
Because they're just predicting words.
Right. They are fundamentally trained to predict the next plausible sequence of words based on a vast training corpus. They are autoregressive.
Meaning they look at what they just wrote and guess what comes next.
Yes. They're not specifically built to maintain an internal, rigorous mathematical model of the physical world.
So they generate text that sounds right?
But not necessarily a plan that is physically possible.
So if they are just predicting the next word, we are essentially relying on a giant autocomplete to build our houses and fly our spaceships.
Which is terrifying when you put it that way.
Very terrifying. Which brings us to the mission of today's deep dive. We are going to unpack this novel architecture that totally flips the script.
It uses the LLM effectively as a translator rather than the sole reasoning engine.
Right. And we will detail the exact prompting strategies the researchers use to make this work, because getting an LLM to output flawless code is notoriously tricky.
to say the least.
We will analyze the rigorous benchmarks where they pitted this architecture against other popular agentic frameworks, including some that you listening are probably using right now.
The benchmark results are really eye-opening.
They really are. We're also going to look at a real-world robot demonstration to see how this handles actual physical embodiment.
Because simulation is one thing, the real world is another.
Exactly. And of course, we will end with our novel notions segment, predicting where this technology is heading next and how you might use it in your own builds.
The shift in perspective here is profound, honestly. We are moving away from the monolithic AI dream.
The idea that one model rules them all.
Yeah, the idea that one massive neural network can and should do absolutely everything. We are moving toward modular AI.
Where the language model is just a piece of the puzzle.
Right. It's just the communicative layer, the front-end user interface of a much more precise underlying system.
Let's start by looking at why the monolithic approach fails so spectacularly. Watching an LLM try to plan a physical task is genuinely like watching a master illusionist whose trick completely falls apart the second you look at it from a slightly different angle.
It really is embarrassing sometimes.
You mentioned the word autoregressive earlier, predicting the next plausible word. I understand how that works for writing an essay, but why does that specific mechanism make them so uniquely bad at acting as autonomous agents in a physical space?
Well, it comes down to the cognitive mechanisms of state tracking and preconditions.
State tracking, okay.
Think about how you or I solve a physical problem in our everyday lives. If I'm in my kitchen and I move a coffee cup from the table to the top shelf, I hold a persistent mental model of that kitchen in my head. As soon as I complete the action, my mental model instantly updates.
The table is now clear.
Exactly. The table is clear, the top shelf is now occupied, and my hand is now empty. I don't have to reread a written description of the kitchen to know this.
Because the state is strictly maintained in your mind.
Yes. But an autoregressive language model doesn't inherently maintain that strict updated state space.
It just has the text.
Right. It looks at the massive block of text it has generated so far, attends to various tokens, and just guesses the next logical word.
So in short horizon tasks where the constraints are loose, that works fine.
Yeah, but in long horizon planning, small physical constraints compound. If you forget that your hand is full on step 2, step 50 is going to be an absolute disaster.
I want to ground this with a specific example from the research, because this is where the failure becomes just glaringly obvious.
The blocks world example.
Huh? Yes. The researchers run the LLM through something called the blocks world domain. For you listening, the setup is beautifully simple, almost deceptively so.
It sounds so easy.
It really does. Imagine you have 5 child's building blocks, number 1 through 5. The fundamental rule of this universe is that you cannot place more than one block directly on top of another block.
Basics physics.
Exactly. Here is the initial state they give the model. Block 5 is on top of block 3. Block 4 is on block 2. Block 2 is on block 1. Block 1 is resting on the table.
So we have a few different stacks.
Right. And block 5 is clear, meaning nothing is resting on top of it. Your robotic arm, the thing moving the blocks, is empty.
Yep.
The goal is to rearrange the specific configuration into a totally new stack. Block 1 needs to end up on block 2, block 3 on block 5, and block 4 on block 1.
On the surface, it sounds like a puzzle a child could solve on the cutting room floor with, like a few minutes of trial and error.
My toddler could probably do it.
Right. But we need to look closely at what the language model actually outputs when asked to solve this. It confidently generates a numbered list of instructions.
And what's step 1?
Step 1. Move block 5 from block 3 to the table.
And as a human reading that, you think, okay, great start. That is a perfectly valid move.
Yeah. Block 5 was clear, the arm was empty, so it picks it up and puts it on the table.
But then look at step 2.
Yeah. The LLM outputs. Move block 3 from block 4 to block 5.
Which requires us to pause and ask a fundamental question. Where on earth did the model get the idea that block 3 was resting on block 4?
Exactly. If we look back at our initial state, block 5 was on block 3. Block 4 was way over on block 2.
The model has completely lost track of the spatial relationships after a single move.
It just invented a new reality because the text sounded plausible.
It sounded like a good step 2.
Right. And it gets worse. By step 3, it says move block 4 from block 2 to the table.
Okay.
And by step 4, it is commanding the robotic arm to move a block that is buried underneath 2 other blocks.
Or it tries to place a block on a space that is already occupied.
The entire plan completely unravels within 3 sentences.
I have an analogy for this, and tell me if this tracks. Building an agent purely out of an LLM is like hiring a highly charismatic, smooth-talking project manager.
Oh, I love this analogy.
You know the exact type. They walk onto the factory floor wearing a nice suit, they sound totally convincing, they use all the right jargon.
They've got the presentation skills.
Right. They sit down and write a beautiful, color-coded, incredibly detailed schedule for the assembly line, but they have absolutely no idea how the heavy machinery actually operates.
They don't know the physics of the factory.
Exactly. So they schedule a single welding machine to be used for 2 completely different car parts at the exact same millisecond.
Or they schedule the painting robot to paint a car before the chassis has even been assembled.
Yes. It looks like a plan, it reads like a plan, the grammar is perfect, but if you actually hand it to the factory workers, it is functionally a disaster. It violates the laws of physics.
That is a highly accurate representation of what is happening under the hood. The LLM fails because it cannot rigorously evaluate preconditions.
Preconditions being the rules of the world.
Yeah. In classical planning, every action has strict preconditions. The precondition for moving block A is that block A must be clear.
Meaning nothing is on it.
Right, and the destination must also be clear, and the robotic arm must be empty.
And the language model forgets that moving a block changes the clear status of the block that was underneath it.
It doesn't update the hidden state variables of the environment in a deterministic way. It just guesses the next token.
So what does this mean for us as builders? The immediate instinct for most engineers right now is to say, well, we just need more training data.
Just scale it up.
Yeah. We just need to scrape more of the internet, find every text describing physical interactions, and feed it into the model.
Maybe fine-tune it on 1 million hours of block stacking transcripts.
Right. But does that work?
The authors of this research call that approach a fool's errand, and I tend to agree.
The fool's errand? Wow.
You are trying to force a probabilistic text generator to approximate a deterministic state machine. It is just the wrong tool for the job.
It's like using a hammer to turn a screw.
Exactly. You wouldn't train a language model on every possible mathematical equation in the known universe just to teach it how to add large numbers.
No, you would just give the language model a calculator and teach it how to press the buttons.
The calculator analogy is perfect. The answer is so simple it hurts. We give the AI a calculator for logic.
That is the core innovation of the architecture proposed here, which they call LLM+P.
LLM+P. It bridges language and logic by introducing a hybrid framework.
It merges the zero-shot translation capabilities of LLMs with the absolute mathematical rigor of classical automated planners.
It lets the LLM do the talking and lets the classical planner do the math.
Let's really explore this architecture, because for a lot of listeners, building with modern Python frameworks, LangChain, and neural networks, the tools the researchers are using might sound like ancient history.
They definitely predate the deep learning boom.
Yeah, you mentioned classical planners, and the research relies heavily on something called PDDL.
Yes, PDDL.
I would bet a significant portion of our audience has never written a single line of PDDL. Can you explain what it is and why it's the secret sauce of this whole framework?
Sure. PDDL stands for the Planning Domain Definition Language.
Planning Domain Definition Language.
Okay, and you are right. It feels like an ancient dialect to modern machine learning engineers.
Yeah.
Because it has been the standardized language of classical AI planning since the late 1990s.
Wow, the 90s.
Yeah, this was the era of symbolic AI long before deep learning took over. But it remains incredibly powerful because it is mathematically formal and entirely deterministic.
It doesn't guess.
Never. PDDL fundamentally consists of 2 separate text files. The first is the domain file. You can think of this as the physics engine of your specific world.
Wait, let me make sure I'm mapping this correctly. Is the domain file essentially acting like the core code in a video game?
That's a great way to put it.
Like, if I'm building a simulation, is the domain file the script that dictates gravity exists, walls are solid, and a character can only hold one item?
That is exactly how to visualize it. The domain file defines the state space, the objects that exist, the actions a robot or agent can take, the strict preconditions for those actions, and the transition functions.
Transition function.
A transition function simply dictates how an action changes the state of the world. It is a lifted representation.
Meaning?
This means it doesn't care if you have 5 blocks or 50 blocks. It just defines the abstract rules of how blocks interact.
Okay, so the domain file is the unchangeable laws of physics. Then what is the second file?
The second part is the problem file.
The problem file.
The problem file provides the specific context for the task at hand. It lists the exact objects you have right now.
Like, for example, it explicitly states I have block 1, block 2, and block 3.
Right. It declares the initial state of those objects, like block 1 is on the table. And crucially, it defines the specific goal conditions you want to achieve, like block 3 is on block 1.
Okay, I understand the two files. The domain is the physics engine. The problem is the specific level you are trying to beat.
Yes.
But how does the agent loop actually work in practice? Because the whole point of an LLM agent is natural language interaction.
We want to just talk to it.
Exactly. We are not expecting a normal user to sit down and write obscure 90s formatting language to get their robot to clean the kitchen. The user just speaks English.
And that is why the pipeline of this hybrid system is elegant, precisely because of its modularity. Let's walk through the exact step.
Okay, step 1.
Step 1. The user provides a natural language command. It can be as casual as, make me a cocktail, or stack these blocks in a reverse order.
Just plain English?
Step 2. The LLM takes that English prompt and translates it into a PDDL problem file. In this step, the LLM is acting purely as a linguistic translator.
I really want to emphasize that for the builders listening. The LLM is not solving the problem.
Not at all.
It is not generating the step-by-step plan. It is only looking at the English words, identifying the constraints in the goal, and mapping them into PDDL syntax.
Exactly. It defers the actual reasoning. Which brings us to step 3. We take that newly generated PDDL problem file, pair it with our pre-existing human-written PDDL domain file.
The physics engine.
Right. And feed both of them into a classical symbolic planner. The researchers use a very well-known open source system called Fast Downward.
Fast downward.
This classical planner doesn't guess. It uses highly efficient deterministic search algorithms to explore the entire state space. It looks at every possible combination of valid moves, and it outputs a mathematically optimal, flawless sequence of actions.
When you say optimal, you mean it actually finds the shortest possible path to the goal, guaranteed by the logic of the system.
Provided a valid path exists, yes. It'll find the most efficient route without hallucinating.
And then what?
And then finally, we have step 4. The classical planner outputs a symbolic PDDL plan, which essentially looks like a list of raw code commands. Something like pick up block 3 or stack block 3, block 1. The LLM takes that raw code and translates it back into conversational natural language for the user.
Or it passes it directly to a robot's motor controllers for execution.
Exactly.
This feels like a massive aha moment. The LLM has been completely relieved of the burden of figuring out the physics of the world.
It's free to just do language.
Yeah, it is doing what it was natively built to do, translating between languages. In this case, translating from English to PDDL, waiting for the calculator to give the answer, and then translating the PDDL back to English.
It is a brilliant reframing of what an LLM should actually be doing in an agent stack.
It really is.
By isolating the LLM's role to pure translation, you are leveraging its massive pre-trained linguistic competence while entirely bypassing its lack of functional competence.
You get the flexibility of interacting in natural language, but you retain the guaranteed logical correctness of 1990s symbolic AI.
It marries the best of both worlds.
That sounds perfect in theory. But getting an LLM to write perfect, mathematically rigorous code in an obscure formatting language isn't exactly trivial.
No, it's very hard.
This is where I want to dig into the prompting strategy, because anyone who has tried to get an LLM to output structured JSON knows it can be an absolute nightmare.
Oh, JSON is easy compared to this.
Right. So PDDL has to be even worse. If the PDDL has even a single syntax error, the classical planner will just crash, won't it?
That is the fragile bridge in this architecture. Classical planners like Fast Downward expect absolute structural perfection. They are entirely rigid.
So a missing comma breaks the whole thing.
A single missing parenthesis, a slightly misspelled variable, or an undefined predicate, and the system throws a fatal error and halts.
Wow.
The researchers discovered very quickly that zero-shot prompting, meaning simply asking the language model to write the PDDL based on the English description without giving it any examples, fails completely.
Let's talk about those specific failures, because knowing how these models break is often more instructive than knowing how they succeed.
Definitely.
In the paper, when they tried zero-shot prompting, even with a highly capable model like GPT-4, the model just started inventing made-up predicates.
It hallucinated the code.
Yeah, for instance, instead of using the predefined state handEmpty, which the domain file explicitly expects, the LLM just decided to make up a new word and wrote empty.
Or it completely missed crucial initial conditions, like forgetting to write down that block 1 was resting on the table.
Why does it do that?
Well, the LLM falls into a very human trap. It assumes the classical planner can just infer missing context the way a human reader would.
Ah, I see.
If I tell you a block is clear, you might naturally assume the hand is empty. A symbolic planner cannot make assumptions. If a variable is not explicitly defined in the initial state, it does not exist.
So zero-shot prompting is entirely out.
Entirely out. The methodology that actually makes this architecture viable relies heavily on in-context learning.
Okay, in-context learning.
This specific prompting strategy is the key to the whole paper.
I'm incredibly curious about this. How many examples do you have to feed this thing to get it to write flawless 90s logic code?
That is the really surprising part. The architecture requires passing exactly one demonstration in the prompt.
Just one. You're telling me a single example is enough to align a massive neural network to a rigid syntax?
Just one. But it is a minimal, structurally perfect example. In the prompt window, you provide a very simple natural language problem for that specific domain.
So what does that look like?
For example, a tiny problem involving just 2 blocks. Following that English description, you provide the corresponding perfectly formatted PDDL translation of that 2-block problem.
And that's it.
That is your entire context window. Then you append the user's new, highly complex natural language problem, maybe involving 20 blocks, and ask the model to generate the new PDDL.
That is wild. With just a single context window example, the LLM successfully maps the linguistic entities from the English prompt to the correct PDDL syntax for entirely new, vastly more complex scenarios.
Yes, it just scales it up.
It looks at the example, sees the mapping of the English phrase, your arm is empty, to the strict syntax arm empty, and suddenly it knows exactly how to format the rest of the file without hallucinating new variables.
What is fascinating here is the underlying cognitive mechanics, for lack of a better term, of the model.
What do you mean?
It is demonstrating a profound ability to recognize the structural pattern of the translation task.
Yeah.
It understands that the spatial relationship on top of maps directly to the on-XY predicate, and it applies that mapping perfectly to the new problem.
It scales it up to handle constraints it has never seen without inventing new syntax.
Exactly.
From a pure engineering standpoint, the efficiency of this is staggering. Think about the alternative.
Fine-tuning.
Yeah. Usually, if we want a model to outcome a highly specific niche coding language flawlessly, we assume we need to fine-tune it. We assume we need to gather thousands of training examples, update the neural weights of a massive multi-billion parameter model, and spend tens of thousands of dollars on compute.
It's a huge undertaking.
But here, you don't need any of that. You just need a well-crafted system prompt with a single golden example. It is incredibly lightweight.
You could deploy this on an edge device's limited context window tomorrow.
It is a massive win for accessibility and rapid iteration. Any developer listening right now could write one simple PDDL example for their specific use case.
Whether that is a robot navigating a cluttered warehouse, a software agent sorting files in a complex directory tree,
or an NPC in a video game managing an inventory.
Exactly. And immediately unlock optimal error-free planning via this hybrid loop.
Okay, that sounds incredibly promising, but does it actually hold up under real pressure?
That's the real test.
Building an agent that can stack a few blocks is a nice toy problem, but if we are talking about enterprise-grade autonomous agents, we want to see this thing sweat.
Oh, the researchers definitely made it sweat.
They didn't stop at blocks. They tested the LLM+P system across 7 notoriously difficult robotic planning domains. We are talking about domains borrowed directly from the international planning competitions, the proving grounds for automated reasoning.
Yes, these are not trivial tasks designed to make the AI look good. These environments are engineered to expose flaws in logic.
Give me some examples. How complex am I talking?
To give you a sense of the complexity, let's break down a few of them. They use the barman domain, where a robot bartender has to mix specific cocktails.
Okay, that sounds fun.
It is, but it requires tracking the states of shakers, shot glasses, ingredient bottles, and the hands holding them.
Lots of variables.
They used floor tile, where robots have to paint a complex grid of tiles without ever stepping on a tile that has wet paint.
Oh, that's tricky.
They use grippers, which is a routing problem involving moving multiple objects between different rooms. They used storage, which involves lifting and dropping heavy crates with specialized hoists in a constrained warehouse space.
And what was the last one?
And the used terms, where a robot builds complex vertical structures by carrying blocks and actually climbing up the structures it is actively building.
That last one sounds like a nightmare to plan. The robot has to build its own staircase while carrying the building material.
Exactly.
So they ran 20 automatically generated, highly complex tasks for each of these 7 domains. We have the ultimate cage match here.
The three-way cage match.
Right. We are comparing 3 approaches. The LLM acting on its own, the LLM using a highly popular deliberate reasoning framework called Tree of Thoughts, and our hybrid LLM+P architecture. Let's look at the baseline first.
The LLM.
Yeah, just asking the model to output the step-by-step plan in plain text. How did it fare?
Dismally.
Dismally.
Across the board, the LLM alone achieved anywhere from a 0% to, at absolute best, a 35% success rate depending on the simplicity of the domain.
Wow.
But in domains with complex compounding spatial relationship, like floor tile or terms, it was a flat 0%. It couldn't generate a single feasible plan out of 20 attempts.
0%. That is sobering for anyone trying to build purely autoregressive agents.
But what about Tree of Thoughts?
Tree of Thoughts.
I feel like every time I open an AI newsletter or browse developer forums, someone is praising Tree of Thoughts as the ultimate agentic reasoning loop. I should probably explain Tree of Thoughts, or TOTI, for the listener.
Please do.
It is a prompting framework where the LLM is asked to essentially expand a search tree. It looks at its current state, generates a list of possible next actions like branches on a tree, evaluates the likelihood of each branch reaching the goal, and essentially tries to simulate a rigorous search algorithm using its own internal text generation.
Right, it's trying to do classical planning, but with language.
It is supposed to be the fix for autoregressive hallucination.
In theory, TOTI sounds exactly like what is needed. It forces the LLM to think step by step, evaluate multiple paths, and backtrack if it hits a dead end.
But in practice,
on these rigorous, physically constrained benchmarks, it was a disaster.
the researchers applied a generous 200-second timeout limit for the agent to find a solution. The Tree of Thoughts approach timed out in almost every single case across the complex domains.
200 seconds of pure computational hallucination.
Yes.
That is an eternity in compute time. Why did it fail so badly when it was explicitly instructed to evaluate its own choices?
Because relying on an LLM to generate and evaluate every single node in a complex decision tree is incredibly inefficient. Think about the computational overhead.
Right? It's making so many calls.
The LLM had to be called at each node just to provide a list of available actions. Then it had to be called again to write a textual evaluation of each new path.
And did it evaluate them well?
What the researchers found was that while the LLM was somewhat decent at ranking partial plans, it could generally guess which direction looked promising in the short term. It fundamentally failed to recognize when it had actually achieved the strict multivariable goal state.
It lacked the rigid mathematical definition of success.
So it would just keep searching, endlessly expanding branches, getting totally lost in its own generated text until the clock ran out.
I call this the inner monologue trap.
The inner monologue trap, yes.
We keep trying to force language models to literally talk their way through complex spatial and temporal constraints as if generating more words equals generating more logic.
And it just doesn't.
I really want to dig into the specific failure modes here because the details are hilarious and illuminating. In the floor tile domain, where the robot has to paint without stepping on wet paint, what did the LLM do?
In floor tile, the LLM acting alone completely violated the rules of physical adjacency.
Meaning what?
It would generate a command telling the robot to paint a tile that it wasn't even standing next to.
Yeah.
It was essentially commanding the robot to use telekinetic powers to paint a tile on the other side of the room.
Just use the force, robot. And what about the temporal failures? The sequencing issues?
We saw severe temporal failures in the barman domain. The goal is to make multiple cocktails using the same equipment. The LLM consistently forgot to command the robot to wash the shot glasses before pouring a new, different drink into them.
Ooh.
Yeah. It understood the conceptual recipe, it knew what ingredients went into the cocktail, but it failed completely to track the chronological state of the physical tools required to execute that recipe over time.
It's the smooth-talking project manager again. They know the cocktail recipe, but they don't realize there's only one shaker in the bar.
Exactly.
So we've seen the LLM fail, and we've seen Tree of Thoughts time out. Let's look at the hybrid architecture. The LLM+P framework utilizing fast downward. What were the success rates on these exact same impossible tasks?
The hybrid system achieved an 85% to 100% success rate across all 7 domains.
That is a massive jump.
And it is crucial to understand that these were not just successful plans, they were mathematically optimal plans. The classical planner guaranteed the shortest possible sequence of actions to achieve the goal.
Wait, if it uses a deterministic solver, why wasn't it 100% across the board? What caused that 15% failure rate in some domains?
The failures were almost entirely translation errors.
Oh, from the LLM.
Right. The LLM occasionally misspecified a detail in the problem file. For example, it might miss a subtle initial condition mentioned in the English prompt, which would render the generated PDDL problem technically unsolvable by the planner.
But if it translated it right?
When the LLM's translation was correct, which was the vast majority of the time, the physical execution of the plan was flawless.
If we connect this to the listener's own experience building agents, the lesson here is profound. Relying on an LLM's inner monologue to handle long-term memory, rigid state constraints, and spatial reasoning is computationally expensive, extremely slow, and highly error-prone.
It's the wrong approach.
Offloading the actual problem-solving to deterministic optimized code is the ultimate cheat code. Stop making the LLM do math. Stop making the LLM simulate physics.
Let it translate human intent into code and let the specialized tools do the actual work.
This does raise a very important question, however. We have proven that this hybrid architecture dominates in text-based benchmarks and simulated competitions. But software benchmarks, even difficult ones, are clean.
Very clean.
The real world is incredibly messy. If we are talking about true agentic AI, we have to ask, how does this architecture handle physical embodiment?
Yes, this brings us to the real-world implications of the paper. This is where the research stops being just a clever software trick and becomes a genuine robotics breakthrough.
They actually put it in a robot.
The researchers didn't just stay in simulation. They actually deployed this LLM+P system on a physical mobile home robot. It's an autonomous robot base equipped with a single gripper arm, and they set it loose in a physical space with real furniture.
The scenario they engineered is a classic tidy-up task, something we eventually want all domestic robots to be capable of.
The holy grail of home robotics.
The human user simply speaks a casual, natural language command to the robot. Move the mustard bottle from the coffee table to the pantry, and throw the empty soup can from the side table into the recycle bin.
I want to help the listener visualize the optimization problem here, because the physical constraints of the robot and the room are key to why the AI succeeded or failed. Let's lay out the map.
Okay, let's map it out.
The robot is currently starting at the coffee table, where the mustard bottle is located. The pantry, where the mustard needs to go, is far away. Let's assign that journey a distance cost of 20.
Cost of 20 to the pantry.
Got it. The side table, where the soup can is located, is roughly halfway to the pantry. We'll give that a distance cost of 10. The recycle bin is next to the side table.
Okay.
And the most crucial constraint of all, the robot only has one single gripper. It can only hold one single object at any given time.
So it can't carry both at once. When the researchers tested the LLM acting alone on this exact physical problem, what happened?
It generated a completely valid but wildly inefficient plan. It told the robot to pick up the mustard bottle at the coffee table, drive all the way to the pantry, incurring a distance cost of $20 down, put the mustard bottle down, then drive all the way back across the room to the side table, incurring another distance cost of 10.
Oh, wow. So much backtracking.
Then it picked up the soup can and threw it in the bin. The total cost of this inefficient sequence was 31.
It's exactly the kind of plan you execute when you're completely exhausted at the end of the day and you're not thinking ahead. You think, I'll just do one chore, finish it entirely, and then start the next chore, even if it means walking back and forth across the house 3 times.
We've all been there.
But the hybrid solution, LLM+P, found something much smarter, didn't it?
Because it leverages a classical planner designed specifically to minimize a metric, in this case, the total cost of travel distance, it searched the state space and found the globally optimal path, bringing the total movement cost down to 22.
Down to 22? How?
The planner recognized the spatial geometry. The side table was directly on the way to the pantry, so it generated the following sequence. Grab the mustard bottle, drive to the side table.
Well, wait, now at this point, the robot has a severe problem. Its single gripper is full holding the mustard, and it needs to grab the soup can.
Here is where the absolute genius of deterministic logic shines. It doesn't get confused by the full gripper. The planner tells the robot to do something highly unintuitive. It tells it to put the mustard bottle down on the side table.
Oh, it temporarily frees the single gripper by utilizing the side table as a staging area.
Exactly. Once the gripper is empty, it grabs the soup can, throws it into the nearby recycle bin, regrasps the mustard bottle from the side table, and finishes the short remaining drive to the pantry.
It inferred a complex, multi-step choreography that required utilizing temporary states, putting an item down just to free a tool, purely to shave points off the total travel distance.
And the robot did this on the fly.
A human engineer did not explicitly program that specific sequence of staging the bottle. The human just walked into the room and said, "Clean up."
The implications for robotics and multi-agent systems here cannot be overstated. You can give a robot a completely task-agnostic domain file, essentially a static document that just outlines its basic physical capabilities, like I can grasp an object, I can drive to a location, I can drop an object.
Just the basic.
Then you let the LLM translate any random, highly complex human request into a problem file. The robot will autonomously infer incredibly complex optimal choreographies without any further human intervention.
It beautifully separates the what from the how. The human dictates the what. The classical planner dictates the how.
It is incredibly powerful.
But I have to push back a little here because no system is perfect, and we owe it to the builders listening to point out the potholes. Let's talk about the blind spots. If I want to implement this tomorrow, what are the actual limitations of this LLM+P architecture as it stands today?
It is a vital question, and the authors themselves are very clear and honest about the limitations. First and foremost, a human expert still has to write the domain PDDL file manually beforehand.
Right.
You have to sit down and formally codify the physics rules, the predicates, and the transition functions of your specific environment. If you are operating in a highly controlled warehouse, that is doable. But if your environment is incredibly dynamic or unstructured, where the physical rules are constantly shifting or unknown, writing a static PDDL domain file is exceptionally difficult.
Right. If you take this tidy-up robot and suddenly drop it into a zero-gravity chamber on a space station where it has never been before, and you don't have a pre-written PDDL file for zero-gravity physics, the entire system breaks down. The LLM cannot magically invent a new physics engine on the fly.
Precisely. It relies entirely on the human-provided logic engine. The second major limitation is the autonomy of invocation.
The routing problem.
Currently, the system relies on humans, or hard-coded scripts, to know when to trigger this specific planning loop. If I ask the LLM, what is the capital of France? It shouldn't try to write a PDDL file.
Obviously not.
The LLM doesn't currently auto-detect, this user's prompt involves spatial reasoning and multi-step constraints. I should route this to my PDDL translator. It requires an explicit architectural trigger.
We see this in agent frameworks all the time. Knowing which tool to use is sometimes harder than using the tool itself.
It's an ongoing area of research.
But even with those limitations, the manual domain writing and the routing issue, the core takeaway for you, the listener, is undeniable. Agentic systems shouldn't just be LLMs talking to themselves in a dark room, hallucinating variables until they time out.
They need tools.
The future of reliable, enterprise-grade agents lies in hybrid architectures. Language models act as universal translators, bridging the messy, ambiguous intent of human language with the cold, hyper-specialized, deterministic precision of classical software tools.
It is a fundamental paradigm shift from monolithic intelligence, where the model is the brain, the memory, and the calculator, to collaborative intelligence. The LLM is simply the interface. The classical algorithms are the engine.
Okay, we have thoroughly covered the architecture. We've broken down the benchmarks. We've analyzed the physical robot demo. It is time for everyone's favorite part of the deep dive. Let's transition to our novel notions segment.
I must state for the record, please note, the following segment is for entertainment purposes only and represents speculative extrapolation of the research.
Thank you for the legal cover. All right, I'm challenging you. We've seen how LLM+P uses PDDL to translate physical blocks in mustard bottles into optimal logical sequences. I want you to pitch me one or two outlandish but entirely plausible agent architectures inspired by this exact PDDL translation concept. Where does this technology go when we scale it beyond robotic arms in living rooms?
Well, if we accept the premise that PDDL can represent the physical rules of block stacking, we have to realize it can represent any system of strict interconnected rules. My first pitch is an architecture we might call the corporate law assassin.
Oh, I highly doubt lawyers are going to like the sound of that. Go on.
Think about corporate law, international finance, and the tax code. It is essentially a highly complex, interconnected set of rules, preconditions, and transition states. It is a logic puzzle.
A very expensive logic puzzle.
You could theoretically build a massive, incredibly dense domain PDDL file that encodes all legal financial maneuvers. The rules for creating shell companies, the preconditions for transferring intellectual property across borders, the jurisdictional tax rates, the capital gains triggers.
So the International Tax Code essentially becomes the physics engine of this agent.
Exactly. The rules of finance are the laws of physics. Then a CEO gives a natural language goal to the LLM interface. Acquire our biggest rival while minimizing our overall capital gains tax to under 5% and ensure the resulting IP ends up in a holding company in Ireland.
The LLM translates that human intent into a complex PDDL problem file.
And then the classical planner takes over.
The deterministic planner searches the multidimensional state space of corporate law.
Yes, it explores millions of permutations and finds the mathematically optimal, technically legal, incredibly convoluted sequence of loopholes, mergers, entity creations, and asset transfers that achieves the goal. A path so complex and non-obvious that an army of human accountants would miss it.
And then the LLM translates that sequence back into natural language and automatically drafts the necessary legal contracts for each step.
That is simultaneously terrifying and brilliant. The LLM handles the unstructured text generation of the actual contracts, but the classical planner guarantees the strict logical legality of the sequence. What is the actual probability we see something like this deployed?
The lucrative nature of tax optimization means people will absolutely try to build this. The primary bottleneck is the formalization process. Codifying the entirety of corporate law into strict binary PDDL logic is vastly harder than formalizing block stacking.
Because law frequently relies on deliberate ambiguities and human interpretation.
But for strict numbers-based tax compliance and routing, it is highly plausible and probably actively being researched.
Okay, I have a second scenario to pitch to you. Let's take it out of the boardroom and into the laboratory. I'm pitching the automated wet lab chemist. We combine this exact LLM+P architecture with an actual, highly automated robotic chemistry lab.
Oh, that makes perfect sense. The domain file in this scenario would be fascinating. It would contain the fundamental rules of chemical synthesis, thermodynamic limits, and the specific hardware constraints of the lab itself. The exact number of pipettes, centrifuges, heaters, and chemical precursors available.
Yes. Imagine this workflow. An LLM is set up to continuously monitor the daily feed of newly published biology and chemistry papers. It reads a brand new paper, identifies a novel target compound that looks highly promising for a drug trial.
And then what?
The LLM uses its linguistic competence to translate that target compound's complex molecular structure into a strict PDDL goal state.
And because the goal state is directly linked to the physical constraints of the robotic lab via the domain file, the classical planner maps out the absolute optimal zero-waste sequence of pipetting, mixing, centrifuging, and heating required to synthesize that exact compound.
By the time the human researchers wake up and come into the lab, the LLM has read the literature, the classical planner has solved the optimal chemistry routing, and the robot has physically manufactured the drug for testing. It completely removes the human trial and error bottleneck from chemical synthesis.
I would actually map the probability of that scenario as very high, likely within the next 1 to 2 years. We already have highly advanced robotic wet labs, and we already have LLMs parsing complex scientific literature.
The pieces are all there.
The missing link was a reliable reasoning engine to connect the two without the AI hallucinating a volatile, dangerous chemical reaction. This hybrid architecture provides that exact safety link.
It is a thrilling timeline to be building in. We're moving so fast.
Which brings us to a final provocative thought to leave you with as we wrap up. We are rapidly building agentic systems that can seamlessly translate human intent into flawless machine logic. We are removing the friction between what we want and the execution of the intricate steps required to get there.
The friction is disappearing.
But as these classical planners become exponentially faster, and as the LLM translators become flawlessly accurate, we have to ask a difficult question. At what point does human language itself, our clumsy, ambiguous ability to clearly articulate our prompts and our goals, become the ultimate bottleneck for the machines?
It is a sobering thought. If the machine can perfectly execute whatever you ask, the only limit to the system's capability is the precision of your asking.
Something to mull over as you sit down to write your next prompt. Thank you for diving deep with us today on Talk Tensors. Remember to subscribe, share this with your fellow builders, and keep pushing the boundaries of what these autonomous agents can do. We will catch you on the next deep dive.